Hello everyone, this is Mr. 13 Things coming at you on whatever channel I care to put this up on, I guess. And this is going to be a real quick hitter coming from the math cab this morning, where in fact we do talk with 7th graders about important and foundational matters of mathematics far beyond 1 plus 1 equals 2. And we start in our brains, like all of us who deal with mathematics and the applied or even in the mathematical world, with some important numbers, those numbers being 13 things, hence the name. And what are they? They're E, they are I, J for the electrical engineers, EI pi, minus 1, 0, 1, the square root of 2, Pythagorean's number, the square root of 3, which we're going to talk about in a little bit, the square root of 5, which is related in many interesting ways to the golden ratio phi, infinity, a matrix, or any matrix A vector X, if you would call it that way, once again coming from and sending you to www.dowesolve, SOLVE for x.com. When you realize X like that means a vector X or a lot of things. Is that 13 things? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 things. And the discussion this morning really had to do with this concept of the square root of 3, and it dawned on me that most of these other numbers, there are some really obvious and fun ways to get at them that are not just definitely just memorizing what they are. For instance, E is somewhere in the order of 2.7182 or something like that. Pi, many people know, is 3.14159, etc. I'm going to go ahead and erase these out because that is not my intent. One has to understand that most of these important numbers are irrational. An irrational number is a number that cannot be expressed as the ratio or as a fraction of whole numbers or integers. So, what are we going to talk about today? We're going to talk about all the cool, interesting ways that, or one interesting way that you can get to each of these numbers where it's possible. And I'm going to do it, if I can, in this format. We'll start with E. We'll bring it down to the bottom of the page here. Real cool definition of E is 1 plus a very small number to a very large power. The way this looks usually is in limits, the limit as n approaches infinity of 1 plus 1 over n to the n power. There are other great ways and very important ways to get at n, but this is one way to get at E. For kids to play around with 1 plus 100th to the 100 power, 1 plus 1,000th to the 1,000th power, and then hone in on the value of E. We'll look at that one, but basically, you have to tie people into the fact that you don't always graph X versus Y. Sometimes you put the real in the imaginary plane, and I is 1 in this direction. So there are different ways to get there. One is to take the number 1 and rotate it 90 degrees to the left. One is to take the number minus 1 and rotate it 90 degrees to the right. And eventually, you'll really going to want to look at I as this idea of rotation. So we'll skip that one. Pi. Interesting that you can't go directly there, but a really interesting and nice way to get, you can't get to pi, but you can get to pi over 4 by taking 1 over 1, if you would, minus a third, plus a fifth, minus a seventh, plus a ninth, minus an 11th, etc., and taking the sum of those. So you can have people play around and get to pi. Minus 1, the opposite of 1, which we'll talk about in a little bit. 0, pretty much 1 divided by a very large number tends to go to 0, so that's the limit. 1, the geometric series when n is less than 1, which looks like 1 plus I'm sorry, it's 1/2 plus 1/4 plus 1/8 plus 1/16 square root of 2. Let me go ahead and erase these out now, because those are just really, you're going to see later on there are a lot of approximations, and students have to realize that as long as they understand that all these numbers you can never get to them exactly. You've taken them to a much higher plane anyway. You can never get exactly to e. It does not exist if you want to think of it that way. Pi does not exist. Depending on your students, that could really engender some good creative thought. So we're all the way to the square root of 2. That's one of my favorites. How can you get an approximation for the square root of 2? You can take 1 over 1. Start with 1 over 1. Take the 1 plus the 1 and put it on the bottom. Take the bottom and the bottom, put them on top. You got 3 here. So now you take the 3 and the 2, you put them on the bottom here. You take the 5 and the 2, you have a 7 there. You're not there yet, but you're getting closer. 7 plus 5 is 12. 12 plus 5 is 17. You're not there yet, but if you take 17 plus 12, you get 29. You take 12 plus 29, you get 41. You're still not there, but you take 41 plus 29, and you get 70. 70 plus 29 gets you to 99/70ths. That's a pretty good approximation, but once again, you can go to infinity and not exactly get to the square root of 2. However, the square root of 2 is much easier to find. Think about the unit circle, and we'll start talking in another video about the circles. If that's the unit circle with a radius of 1, a diameter 2, we go across here to here. This diagonal distance here is the square root of 2, and you probably started that way anyway when you start thinking about it. The square root of 3, there is not a good way to get it, so we're going to skip that one and come back to it. There is a really great way to do it by picture, but in terms of a sequence or series, not that I've found. Square root of 5 and phi kind of come together because, in fact, another great series is the Fibonacci series, made famous amongst other places in Mr. Megorium's Magic Emporium, and it begins this: 0, 1, 1, 2, 3, 5. What you're doing is you're adding the 2 previous values in a series. So 5 and 3 is 8, 8 and 5 is 13, 13 and 5 is 21. What's great about this series, it goes from being an addition series to a multiplicative series in a little bit here. 13 and 21 is, let's make sure we're okay there, 21 and 13 is 34. Many people have these memorized. 55. After that, from 55, you go to 89. These next series are the ones that are kind of the neatest. 144, and then you add those 2 together, you get 233. You add those together, you get 377. You get those together, you get 610. So what is, this is actually the value, not for the square root of 5, but for phi. Phi is approximated as, but it gets better as you go along the sequence. The ratio of one number to the previous number in the Fibonacci series beyond the 13th term gets you phi. What is phi, however? Phi is equal to, or the golden ratio equal to that, what is also equal to the average of the square root of 5 and 1. That's what phi is. So check, check. Of course, this one is my favorite, infinity. The closest thing we got to infinity is either 1 over 0, the limit, or better yet, the limit as n approaches 0 of 1 over n is infinity. My favorite, however, is the tangent of 90 degrees, or the limit for that. So we've got this one covered, all of these covered, except now for the square root of 3. To review, pi is 1 minus a third plus a fifth minus a seventh multiplied by 4 gets you pi. 1 plus a very small number to an infinite power gets you e. I is a rotation 90 degrees in the complex plane of either 1 or minus 1. And we're going to go now to the square root of 3 because there is no great sequencer series that I know of or I found that does the square root of 3, but there is a great picture, and the picture is taken as such. Always and early we should be showing numbers as pictures and letting students walk them out, draw them out, do them out, and let them understand that in many ways the pictures are more correct than the numbers as the Greeks originally knew. So what I'm going to do is I'm going to now draw, ooh, I'll do it this way, cool. Draw the unit circle with dots. Okay, that's the unit circle, and now I'll go ahead and draw that kind of center there. The radius of this is 1, r equals 1, and I'm going to draw the first quadrant. Draw the first quadrant, have students divide it in half somehow, and then take a line that goes up through there. If they take the extended line from here, they know that this is the square root of 3. Once again, you take a unit circle. The radius is 1. You divide the first quadrant. You put the kind of axes there. You divide this up in half and half. Students eventually learn that this is 60 degrees or pi over 3. This is 30 degrees or pi over 6. And right down the middle is pi over 4. However, if you take this line, extend it through to there, that length is the square root of 3. But probably better, and at the same time, you can just demonstrate with a $5 laser that if your length is 1, that length there is also the square root of 3. Thanks for listening.